Hello. We'll solve this question. Now, you see, there is this rod of mass 2m and the length L. And there is this point mass of m mass and its speed is v. And this rod is not hinged. This is the center of mass actually. This rod is placed on a horizontal surface. This is not vertical, it is on a horizontal. It's placed on a table. And this point mass is also moving onto the table. This is the horizontal plane we are talking about. So this rod is placed on a table, mass 2m and the length L. This point mass of mass m and the velocity v, it collides with the rod, and after the collision, this point mass comes to rest. It does not stick to the rod, it comes to the rest. And obviously it is coming to the rest, so the rod will start moving. And since this rod is not a hinge, it's not hinged anywhere, so to define the motion of this rod, we have to take two variables. One variable I'll take the velocity of center of mass, and the other variable I'll take as the omega for this rod. So after the collision, this rod, the center of mass of the rod gains VCM, and the rod gains omega. We have to calculate these two values, meaning what will be the velocity of center of mass and what will be the omega after the collision. The given values are final velocity becomes 0, initial velocity is given. Okay, so we have to calculate. So now you can see there is no hinge there. Since there is no hinge there, we can go for conservation of linear momentum. So if you see the whole system, for whole system, and when I say whole system, I mean the point mass as well as this rod. So during collision, there are two forces which are acting. There is no hinge, so there is no hinge reaction. So the rod applies the reaction force onto the point mass, and the point mass applies the reaction force onto the rod. They are action-reaction pairs. So for the whole system, if you see, the net external force is 0. And since F external is 0, it means the momentum for whole system 1 plus 2 will be, conserved. Not 0, it will be conserved. Okay, so let's write that. Let's use that. Since momentum for whole system is conserved, so I can say initial momentum for the whole system and the final momentum for the whole system will be same. So let's calculate the initial momentum and the final momentum of the system. We are talking about the linear momentum first. So initial momentum, if you see, that's m into v, mv, I cap. I'm taking this direction as I cap. And that is equals to final momentum, since initially the rod is not moving. So that's why. And this point mass, you see, the point mass comes to rest. So final momentum of the point mass becomes 0. Plus this rod gains some velocity. So it will be equals to 2m VCM I cap. So that becomes your equation from linear momentum. So if you equate these two things, the VCM comes out to be v by 2. So after the collision, the center of mass of the rod gains v by 2 velocity. So half of the velocity gets transferred to the center of mass. Okay. So this we get from conservation of linear momentum. Now let's go for torque. Now when it comes to the torque, this is the axis I'll assume. So I'm assuming the axis just adjacent to the center of mass of the rod. That we do because we want to make the equations little bit easy. So this is my axis I'm assuming, because if you want to apply this conservation of angular momentum, you have to select the axis first. So this is my axis. I'm calling this axis as O. So about this axis, about the axis O, if I calculate the net torque acting onto the whole system, it is 0. Not just this. Any axis you select onto the ground, the net torque acting onto the whole system will be 0, because there are only two forces which are acting, this one and this one. And they're acting at the same point. So because they're acting at the same point about any axis onto the ground, onto the inertial frame, the r vector will be same. And since they are in opposite direction, they'll always cancel out each other. So because of that, we can say initial angular momentum for whole system will be equals to the final angular momentum for the whole system. So let's calculate that. So if I calculate the initial angular momentum for the system, you see, this is L by 4. So due to the point mass, we can write linear momentum multiplied with L by 4. And that is in anti-clockwise direction. Rod is at rest. So after the collision, this point mass comes to the rest. And you see, so there are two things. The center of mass is moving with VCM and it is rotating with omega. So since this is my axis, then linear momentum for this rod mass will pass through the axis. Since this linear momentum of the rod. So you see, rigid body which is not hinged. The formula for that is R cross PCM plus ICM omega. That's the formula for angular momentum of the rigid body which is not hinged. So MVL by 4 in anticlockwise direction will be equals to R cross PCM. PCM will be in this direction. So PCM will be passing through the axis. Due to that, the sole value, since we have selected the axis just nearby to the center of mass of the rod, the sole value becomes 0. Plus, this is the rod. ICM for the rod is ml square by 12 multiplied with omega. That was the reason. Since body is not hinged, I am selecting my axis just nearby to the center of mass of the rod. Because of that, this whole quantity becomes 0. The equation becomes easy. And this omega also we have assumed in the anticlockwise direction, so that's why. So see, MVL by 4 is equals to ml square by 12 times of omega. M and L gets cancelled out. So omega becomes, you see, this 3 times 3V by L. So when this point mass strikes with the rod, which is placed onto the horizontal plane, there is no friction anywhere. Then after the collision, this rod, center of mass of rod gains this velocity and the rod gains this angular velocity. The main thing is how we are solving this equation. Since we don't see any axis, we don't see this system to be hinged anywhere, we can use linear momentum as well as the angular momentum. You see, so with the use of linear momentum, we can calculate, most of the time we can calculate the center of mass velocity, and with the use of this, we can calculate the omega. Okay. Thank you.